reject this problem.
Okay. Secondly, we challenge Switzerland on problem number 8, levitating fluid.
We accept this challenge.
Okay.
So it was problem number 8, right? 8. Yes. Thank you.
Somebody's sitting there.
Ah.
I'm going to leave it
But
for
you
her.
could just place your chair there. So because the door is going.
Sure.
Es ist die von 80, 40. Macht ihr was?
There is the second picture where
Please start your presentation.
Yes, thank you. So, welcome everybody. Today I'll present number 8, levitating fluid. And this is our class segment. So when a container is partially filled with liquid, when it is oscillated vertically and air is injected at the bottom of the container, the fluid can levitate. And the task was to investigate this phenomenon. So the first interpretation that I had was basically that you have to explain the phenomenon quantitatively, so how and when it occurs and which conditions are given. And then you should investigate basically how you can control the state of levitation, so when it should occur. So first of all, I have here a demonstration video. So when you reach these conditions, so when you enter the stable state of levitation and you have oscillated at a harmonic rate, so you don't change the oscillation, it will remain in this stable state indefinitely. So you see it has this constant behavior. So first of all, let's look at what state we have. So as the problem statement states, you have basically a layer of liquid with a higher density levitating over a layer of air. And as you can imagine, this is usually an unstable configuration. So you've got a large difference of density, and it will usually become unstable since small disturbances like small oscillations on the interface will become greater, so exponentially grow from small amplitudes to large amplitudes, and the interface area will grow, so the stability will grow, as you can see here, right? Here. So it will grow, remaining with this shape, and then you will have like drops and plumes that form, so you'll have the liquid that will go down and due to its gravitational force, and the bubble of air will just tend to go up. So we have, as you can see, two main categories of force that play at hand. So on one half, we got the surface tension force, which basically restores the interface. So it wants to minimize the interface surface. So it will try to pull it back to a stable state. And then we've got the gravitational force that basically drags the denser fluid downwards. So there are certain conditions to when that can occur. So basically, you want to have those forces, so gravitational force, to become more important than the surface tension force that should minimize the effect. So there, basically, the difference of density really plays a big role. So you want to have a large difference of density, and also large waves, so a small number of waves in that interval. So defining these conditions, you can find the critical length of the system. So basically, the length that is necessary for two fluids of different densities and a certain surface tension, which is the minimal length that you need to have in order to become unstable. So for this case, so we use silicon oil and of a specific density, and with the air density, we get this critical length, so 1.5 millimeters, around 1.5 millimeters. So if you've got a capillary that has a smaller diameter, then it will remain stable whatever you do. So you don't have to excitate it to get a stable state. That's important. So in our case, we basically had a container that has a larger diameter. So in our first case, we had a diameter of 3 millimeters, which is 3 centimeters, which is of course larger than this critical length. So now is the question: when you have this unstable configuration, so this destabilizing state, what can you do to basically reach this stable condition? And that's why we basically oscillate this entire system. So we, additionally to the gravitational force, so the acceleration downwards that you usually have, we add a harmonic oscillation with the shaker. So we basically add an additional acceleration. So what is required? So we need rapid oscillation. So the shaker must oscillate, be faster than the time it basically takes for the liquid to fall, so that it can basically stop this behavior before it increases exponentially and then falls. So you want to control it. And you also want large oscillations, so a large acceleration of the system, so that it can compared to gravity. So you basically then have, for the system, for the layer of liquid, an effective gravity that works against the downwards, the gravitational force that you then have. So we have a non-inertial system, so right there. So when you have the gravity and the additional acceleration of the system, we should have afterwards a net stabilizing effect, because when the entire system accelerates downwards on that state, any disturbances on the surface will be flattened out. So it will minimize the disturbances that occurred when accelerated upwards. And this effect will be more important over time, since we're talking about large time scales, than the deformations that you have here. So you will have a stable state due to that. So we work on the interface in that case. So yeah, and this you can basically then look by looking at the acceleration that is acting on the vertical of that state. And as you can see, then you have certain conditions that involve the amplitude of the oscillation and basically the critical length that I mentioned above. So this was our setup. So the setup we worked here, and our great advantage was that we used this shaker that you can see in the middle. So with the shaker, we could basically accelerate our entire system to great accelerations of, let's say, up to 9G. And additionally to that, it's a damped system, so we could have a harmonic oscillation that was really good to work on, and we could shift the frequencies and also the strength of the acceleration. And we measured everything with an accelerometer, as well as tracking the different layers on top. So we basically tracked this area where you have the levitating cushion, and we had a syringe to inject the air from below. So we could control the volume of the air. So here you can see our results for by injecting 10 millimeters of air. So with that specific volume, we then changed the frequencies, and as you can see, there is a great difference between the amplitude of the lower layer, so the interface you have there before, the normal state of the liquid, and then the air above, and the case of the upper interface of the levitating liquid layer. So as you can see, it's a lot larger, which makes sense because you have basically the case we had before, so the disturbances are expected to be higher up. And as you can see, we then basically model this the trend using this theory above. So we got this theoretical line. As you can see, it's clearly above the driving acceleration, but at the same time, it's lower than the actual amplitude we get. So that's because we additionally have the effect of the air layer, since air is like compressible, working as a spring mass system. So it will basically compress and release according to the driving harmonic oscillation. And as that, it has a certain resonance. So when that resonance frequency is reached, it will maximize and amplify the oscillation and work to basically add this stabilizing effect. So you will have like a higher acceleration of the liquid layer on top, additionally to that as well. And this we investigated by basically tracking the volume of the air. As you can see, there are fluctuations of the volume that correspond to the driving oscillation, and although there are differences due to measurement errors, you can see that the trend is approximately constant, and therefore we can see that the air layer behaves that way. And yeah, you can see that we basically track that. Now, additionally to that, we also changed the setup. So we made a larger setup with a larger length of 6 centimeters to minimize the border effects, because as we can maybe talk about them later, they do impact the experiments in a way that we cannot take into account in our theory, so we want to minimize them, so we increase the layer, and on that case, we injected the air from below, but it still worked, since in the stable state it will maintain this case, so it didn't affect to inject it up. And we also, when we measured the least acceleration needed to reach a stable state, as you can see, what is interesting is that from a certain point, so between 40 and 60, the acceleration needed drops like significantly, and this is because of the resonance of the air pocket. So around 50, the system resonates, and therefore the acceleration needed to get it to a stable state is a lot lower from that point. So as you can see, it has an effect. And here we also measure the amplitude of the upper interface and the driven amplitude. And here again, you can see that there's a difference between those interfaces. And here again, you have like a peak at around 50. So at the so where you have the resonance. So now to the conclusion. We basically managed to look at the effects that play a role here, so the forces, and also the effect of the acceleration of the system that we do manage to get with the shaker. So we managed to see that it has an effect in stabilizing the upper interface and therefore in reaching this levitation. And then we also looked at the air cushion, so how it behaves as a spring and varies in its volume. Yes, and therefore, and afterwards we also applied a theoretical model and explained why there's this large difference between the theoretical prediction and the actual measurements due to the air pressure. So that would be my presentation.
Thank you very much. So I want to ask the opponent to give some questions to the report.
Okay. First, did you vary the type of liquid that you used? We used silicon oil, and we also used in the preliminary measurements sunflower oil, but due to the lower viscosity, it would basically go to.
Did you vary the shape of the container that you used?
Yes. So I had before like a circular container of circular shape, and then a rectangular one.
Thank you. Did you investigate cohesion?
What do you mean?
So with the edges of the container.
So I mentioned the edge effect, so that's why I made the container larger so that they play a lesser role.
Did you investigate vorticity?
Vorticity?
So like rotation of the liquid molecules within the system?
I don't think they are relevant, no.
Okay. Did you assume that this was an antibiotic system, or did you investigate any kind of expansion of the liquid?
No.
Okay. Do you think any other forces were at play? Could you go to slide 8?
Slide 8.
Other than gravitational forces such as surface tension, or?
I said surface tension is in the model. So.
Okay, thank you. Could you briefly describe or define the driven acceleration, the driving acceleration?
I measured it with the accelerometer, so it was a given value.
So it is the amplitude you are adding to the system when you say driven amplitude? Or?
Basically, the acceleration causes a certain amplitude on the interface, but it's not, the acceleration is not equal to the amplitude.
Okay, if you could go to, sorry, did you account for any type of bubbles in the liquid layer of the interface?
You mean in the liquid, right?
Yes.
So the small bubbles in this, no, because the time rate we worked in didn't allow like for great changes in
So I think the following questions will be have to discuss in discussion then.
Okay.
So I'd like to prepare you the opposition now.
We can start now.
Yeah, we start the presentation now, please.
Okay. Well, first we talked about the problem description. When a container partially filled with liquid is oscillated vertically and air is injected into the bottom, the fluid will levitate. And they investigated the parameters which affect this phenomenon, mainly the viscosity and properties of the liquid. So for this problem, we expect them to investigate the amplitude of vibration as well as the frequency, the pressure and velocity, or other characteristics of the air being added to the system. We would also like them to thoroughly explain the water pressure as a function of the size of the container, as well as the edge conditions, which would change as the size or shape of the container changes. We would also like to see a large variety of liquids being used as the fluid with a large range of viscosities, which would definitely affect the phenomenon extremely. To summarize the report, they did have a completely sealed system, which we like. They had a manual air injection, and they did measure their measurement error. They observed that and they kept track of that. They did vary multiple things that we were looking for, like the amplitude, the frequency, the size of the container, but there was a limited range of variables, and we think that different types of liquid or more types of liquid with a larger range of viscosities could have made some of their presentation stronger. There was also some unclear parameters, not sure exactly what they varied or how much they varied it, such as which frequencies were tested, which amplitudes were tested. Their theory overall was very good. We think they had a very thorough investigation of the stable versus unstable period of motion. They investigated the parameters which would cause stable conditions. They also thoroughly explained how the density of the air and the density of the liquid relate to the destabling configuration, and how the density must be a certain ratio in order for this phenomenon to work. The capillary with a small diameter is more stable. We agree with their explanation of that. We also agree with the fact that the high frequency works against the gravitational force. We definitely agree with their explanation of the forces, the surface tension, and the gravity, which we clarified in one of our questions. We think that they could have investigated more of the unstable investigation, and once again, this comes back to the limited range of viscosities and edge conditions which were investigated. The boundary conditions on the mathematical model were a large part of the problem, and we think that they could have been investigated more. I also think that vorticity could have been relevant in this problem, and I would like to discuss that further. I think it could have affected the properties of the water, how it was moving, and definitely would have contributed to that unstable section of this phenomenon. I would also like to talk a little bit about the behavior of any air that would be present in the interface layer. As air is being continuously added, it would have to come out somewhere. So, conclusion for the points that I would like to discuss, I mentioned before, I would like to discuss vorticity, some theoretical predictions, a discussion on how velocity would change. I would like to discuss the possible addition of Faraday waves or nonlinear motion into their mathematical model. I would also like to talk about any mathematical assumptions that they made in their physics model, like justifications for simple harmonic motion. I also would like to clarify and talk about their model as air compression as a sort of compressible string. So if we can move on to the discussion. Okay, the first thing I would like to talk about is the edge conditions. You mentioned that you did not include them at all in your mathematical model.
What do you mean edge conditions?
Like around the edges of the container with the liquid on the side.
As you said, that's why we changed the container. So I mentioned mentioned it like positively, and also but with measuring the volume, you saw that I simplified it as having this air pocket, and here this portion that is basically a small plume of liquid in the middle. So there are like actually border effects around it. So the region in the middle will basically oscillate as we expect the layer to do, but there basically the liquid due to adherence will stick to the container and basically have the same amplitude as the lower interface, so it will follow the movement. So only here this part is basically really like oscillating freely, so that's why we basically had this. So that's why we, with the small containers of only 3 centimeters in diameter, the border effects are much more important than if you have a larger container of 6 centimeters, for example, in diameter. So you've got more area that's like
the edge effects, but using a larger container, obviously
if I say it qualitatively, yeah.
okay, not with mathematical model, but
I don't see how you could like, with accordance to the task segment, you could really in an approachable way analyze it, since it's like there are complex equations.
okay, I actually agree with that. So just for the qualitative understanding, that would be because of the cohesion of the liquid, or
Yeah,
because of the
basically
oscillation?
adheres. So yeah, the silicon oil adheres to the surface of the container. So we had like plexiglass as a material, and it will stick to it on the border. So there will have some effects to it. Yeah.
Okay. And then with the air in that layer, now that we're talking about the interfaces, so if I'm understanding correctly, there would be air passing through the higher liquid layer. If you're pumping air into the bottom,
Yeah.
the
So
bubbles.
maybe I should explain how it happens. So basically, we inject it from the bottom, so it will rise due to buoyancy. At a certain point, it will reach like a layer of liquid that perfectly compensates like from the mass distribution the air pocket that goes below. So it will reach a certain stability point where there's a perfect ratio between the air pocket and the layer on top.
So you're
it
saying
will carry
air
it.
is not exiting that pocket at all?
No, what can happen though if you have like a very strong oscillation is will basically mix everything. So there might be small bubbles that go into it at some point. So you will see, for example, in some videos that it's like.
Okay, but
we don't have like those large.
you don't think the bubbles in the air,
negligible, yeah.
in the liquid interface would affect the behavior
In
of the
the
liquid at all?
liquid interface, it has not.
Okay, do you think there are no bubbles, or do you think it wouldn't affect?
There are microscopic bubbles, but
Okay.
it's really on the interface, and it did not affect like our experiments.
And this is mainly in that optimal phase where the amplitude is not too large, you're saying?
What do you mean?
So if the oscillations become too great, the air and the water will be mixed, right? And if it's too small, the phenomenon does not occur.
But even if it's mixed, it doesn't have that important an effect that it really plays a role in our case.
Oh, really? So you're saying even though there's large amounts of air in the liquid interface?
What do you define by large amounts of air?
Well, you said there would be microscopic, right? But if the water and the air are mixing, I would call that at least.
It's very hard to quantitatively describe that because, as you see, it really depends on the case, how large your air bubble is, how on the oscillation. So it's very hard. I mean, how would you define it? Just by the coloring of the video, or like?
Well, I would assume it would be based on, like you mentioned, the amplitude and the oscillation as well as the amount of air you're putting into it. So although I'm not familiar with an equation that could predict that, I'm sure there's some way of quantifying the amount of air that would interact with water.
Yeah, so what exactly do you mean by the air in the interface?
Like any sort of bubbles or air that would be interacting with the water itself, not just at the bottom edge.
I don't know, I find it hard to understand how to like quantify it. It's because it's hard to say, okay, this is oil and there's air, so you may basically what I assume you say is that it mixes at some point, but that's hard to say at which point exactly and where that happens.
So you're saying you're not able to quantitatively explain it.
No,
Although
I don't. If you have any suggestions, I would be glad to have them. But I don't see how you could possibly do that.
Okay, so if you could remind me which liquids you used and if you calculated the viscosity of this?
Yes, I can go. So we used silicon oil, and we did preliminary experiments trying to basically see when we can reach this stage. So we use silicon oil, and we measure the kinematic viscosity. So we use a specific silicon oil here, and so we basically needed to have a fluid with a high enough viscosity to basically reach this stable state. So if you use, for example, let's say honey or silicon oil or any fluid that has a surface tension that is not high enough, it will basically break and not sustain high accelerations. And if you have something like, let's say, water, it will basically directly go into Faraday instability and just splash. So you won't have that stable, it will not sustain those oscillations.
So did you investigate those Faraday nonlinear motion
I say
at all?
it was not in the task statement. So I basically reproduced the phenomenon, and the only way to reproduce the phenomenon in the conditions we had, so with those isolation, was with silicon oil. I couldn't reproduce it. There was no way you could do it with any other.
You don't think that you could have used a higher viscosity, like you mentioned, something like honey would have worked in this case?
No, honey would not have worked.
Would not have worked.
Essentially
Oh, okay, sorry, I
high.
misunderstood you. Could you? So the high viscosity would not work. The amplitude wouldn't be great
No,
enough.
if you have a very, let's say, a liquid with like very high viscosity and high surface tension and everything, you need like very high, so we basically need something that has a stable surface between the air and the oil or the liquid, right?
Okay.
So if it's too high, you basically need extremely high accelerations to even like get it to respond.
I
So
do agree that using those
Or
extremes
limited
would have
by
worked, but I think you could have investigated a slightly larger, maybe using different kinds of oil in your experiment. Do you think that the difference in viscosity would have been enough to affect your mathematical model?
No. It basically enables this to happen, but the viscosity does not play a role in basically sustaining this oscillation. So what really plays a role is the surface tension at the interface, at the upper interface.
So, but wouldn't changing the liquid also affect the surface tension?
Those are separate fluid properties. So you can have like a fluid that has a higher viscosity but lower surface tension, or like for example, let's say honey would be an example. So it's really, you can't interchange those two properties, and it's really, I don't know, I didn't investigate it also because it's not in the task specifically. So
But you think that the surface tension is important, and if you varied it, it
surface
wouldn't
tension
make a
is
difference?
important.
Okay,
Yeah.
but viscosity you're saying wouldn't have.
No, as long as you can reproduce the phenomenon, so when you have these conditions, so basically if the viscosity is too low, you will have Faraday instability, so
I agree with you
very
on that.
high amplitudes.
But I think that
and
the
you can't sustain
range
that.
of viscosities that would have worked is slightly larger than what you're saying, with a very narrow type of liquid such as oil.
Yeah, I said it's like not in the task, so of course you could have varied it, but it wouldn't be a really relevant parameter when we're looking at the specific behavior. So you would, no, I don't think
Okay.
it would have played it.
I think we can move on. Could you go to the beginning when you had the video demonstration of the phenomenon?
Yeah.
Okay, because I see in several of your diagrams you have like the waves at the bottom, and
What do you mean? Yeah.
like,
Yeah.
so and you're
There wasn't
talking about
anything.
right, like simple harmonic motion and stuff here. Do you have any like more quantitative justifications for
So
this?
basically we've got the driven acceleration of the system, and that's why we basically use this shaker. So it has this dash motion, and it can like accelerate upwards in a harmonic way, and we had the basically the sensor that could track this movement, and then we fitted it with a
Sorry, so
sinus curve.
when you're tracking it, you're tracking the water itself?
No, we're also tracking basically what we're tracking is this interface, so the lower interface that is interface with the driven acceleration, and then also the interface that is hanging above the air. So this one and this one. You understand?
Yes, I do understand. Is there any math where you made like any assumptions that we did not talk about? I didn't get a chance to ask about it earlier, but like assumptions in your math, such as the ignoring the edge conditions when you make a larger.
Yes, of course. I said we do not take into account those like the edge conditions that I think listed up. That's why we maximize of course it's like an ideal model. So we basically look at which conditions should hold, but then there are of course like edge effects that are like hard to quantify in this setting. Yeah.
Did you attempt to quantify them at all, or?
Not really.
Okay. You mentioned that you're treating the compressive air layer sort of as a compressed string. Is that in terms of the energy for, or like what exactly
So-
is the explanation?
Yeah, basically how it behaves. So when you accelerate the system, it will be compressed between the two liquid layer, and then when you accelerate the downwards, it will relax. So it will basically, since air is compressible, not like let's say water or silicon oil. In this ideal case, it will respond, and it will
You should come to
basically
me now.
yeah.
Okay.
Okay, thank you very much. You could now please summarize your
Okay.
discussion.
In summary, I do think, sorry, could you restart and see the time? I do think we had a very productive discussion. I clarified a couple of parameters that I did not quite understand exactly how she investigated. Overall, I think the type of parameters they investigated were very good. I do think that a larger range of viscosities, different kinds of fluids. I disagree with the narrow range that they were using. I think that changing the surface tension or changing the viscosity that was used would have affected the problem. I also think that there was very limited investigation into the edge conditions, but I do agree that it's hard to quantitatively explain these things. Same with the bubble effects, although I do think we agree that while these things could make a difference in the phenomenon, I agree they are very difficult to quantitatively explain. I think our discussion overall, especially relating to viscosity, was very eye-opening for me, and I'm glad that we were able to come to these conclusions. Thank you.
Okay, thank you very much. So questions from the reviewer now, please.
Thank you for insightful discussion. So, the opponent, you mentioned the boundary effect in the discussion, right? What do you think about what is the boundary condition?
The boundary conditions at the edges of the container?
Yeah, what are you talking about?
I was talking about the adhesion of the liquid to the container.
Oh, so do you think it will be related to the material of the container?
Yes.
Do you think the material of the container will be affected?
So it's basically corrosion. So it's how. So it's about the.
Yeah, it's the idea of wetting, which I think is quite important. And so why can you explain in the phenomenon and why so normally without oscillation, if you pump air bubble, it will rise. But why under oscillation the bubble would not rise in the oscillation? Can you explain it simply?
So it will basically. So I say at the interface, the interface will be stable due to the acceleration. It will limit it will make it more stable, so it will have a harder time basically.
Oh, it's harder to go up.
Yeah.
Okay. So I think in the short question, you both agreed with the surface tension force and the gravitational force. But the viscosity of the thing that she used is quite big. So do you think viscous force should be considered? Viscosity force?
I don't think it's necessarily though.
And do you think okay, no. And okay, so you said vorticity is important. Why do you think vorticity is important?
I think especially when you're discussing the unstable conditions.
Yeah, but I thought for me vorticity needs to have it has to rotate, and it is obviously not happening in. Are you talking about like vortex?
Look, I think vorticity, like the non-linear sort of motion, I think.
Yeah, but
Of
okay.
the molecules.
Sure. So it's good that you clarified the viscosity, but have you had any measurements for the surface tension of the oil you use?
Surface tension, we use silicon oil, which is a scientifically used material. So we had all the properties given by the manufacturer, and there no easy way to basically measure surface
So
tension.
yeah, so you only measure the kinematic viscosity, correct? That's the measurement or from the.
Yeah, that's the kinematic viscosity we measured like preliminary.
Okay, and in your report, it's just this page. So you think from the video, I think there will be some small perturbations on the surface, but you only said it will have these two big waves.
So that's basically a very qualitative demonstration. So a very simple case where you only have one wavelength in it. But of course, when you have, that's why I have it. You have like you have a way larger wave number on the interface of the surface. So that's a very simple stage.
So will this be important in the actual levitating effect?
Of course, yeah. If you have a larger wave number and of a smaller size, it will be much more stable than if you have very large waves and very little waves.
Okay, thank you. Final question. So you said the compressibility of air. Do you think it will be an adiabatic process or no?
I don't think so.
Okay, yeah. 要讲YT。
Could you please connect to that?
Hello everyone, I'm a reviewer from Team Taiwan, reviewing problem number 8, levitating fluid. So here's the problem recap of levitating fluid. So here are the key questions I think is quite important. So first, you need to clarify the effect of oscillation of the effect gravity modulating. And about the air bubble not rising, where I clarify from the reporter and get a good explanation. And then for accounting for a fluid surface as a small perturbation, as the reporter does not have a good equation for that. And then the parameters that changes the time scale of the dripping, because the time scale is most important, and the effect of fluid wetting, which I first asked in the questions. So here's a reviewer report. So she uses silicone oil will levitate when it is oscillated and she explained it by using a Rayleigh-Taylor instability of the density difference, making it flip over in the non-oscillation condition. And then she also explained the capillary length is a condition where the fluid will not drip down. So first, she has a successful levitation, which I think is quite good because this experiment is quite hard. And also, she explained the concept of Rayleigh-Taylor instability, which is the main phenomenon causing the shift in the density of different fluids. And also clarify the capillary length will not drip down. This is when she discussed the limits, because when the container is too small, the fluid will kind of levitate if it's not oscillated, because the capillary will always pull over the gravity. But she did not clarify the viscosity and surface tension of the fluid. Only the opponent had pointed out later in the discussion, which I think is quite important. She should let us know. And she should explain the importance of air bubbles staying in the bottom of the container. For during the model, she mentioned the modulation of gravity will stabilize the surface, and the surface will be flattened out. And she compared the surface tension and the effective gravity. And she has a gravity modulation, which I think is the most important forces. But I think for a model, we should tell us the time scale of the dripping down. Because if the time scale is long, the oscillation does not need to be very big. But the time scale drifts very fast into very big oscillation. And I think she should have a better small surface perturbation model, accounting for a surface change. Then for experiments, she has parameters of frequency, amplitude, and the shape of the container. I think she did important parameters, and the setup is quite good. But I think the viscosity and wetting is very important in the phenomenon, where changing the viscosity will change the time scale, and the wetting is also very important, and the theory line does not predict too well. For data analysis, she said the air acts like the spring, and I think however there will be large deviations. So I thought it is a very good qualitative explanation about the air volume changing over time, which I think she tracked it is very good. But I think she can calculate the resonance frequency from the theory, and the sine waves does not fit. So for opposition, she presented. I think she first talked about vorticity, which I don't think is that important because I don't think anything is spinning inside. And for a short question, she clarified the fluid, but she did not obtain the value of the viscosity and surface tension. But it's a good thing that she noticed the gas expansion. So that is quite important because she is using a model. Okay, and for discussion, I think she is good at discussing the edge of the container, but I think there will be more points I'll be later talking about. From this point, they missed out the importance of the fluid wetting the container and the viscous forces because the viscous of the oil is quite big, and the time scale for dripping and also the pressure over time. So the first discussion is about the condition near the edge, where the reporters think that is not, they both agree that's important, and I think it's the most dominant result, because when the fluid is wetted, the fluid could just literally drip down, and if it's not wetted, this could levitate. Then also, I'll talk about the bubbles inside the liquid layer, and the report said it will have very small bubble, but she did not explain why the bubble didn't rise, as I clarified it in the short questions. And then they talk about the effect of viscosity. I think the force of the viscosity should be considered because it's quite strong in the oil she used. And this is the end of my, thank you.
So thank you for the opponent and the reviewer. So first of all, I would like to say that I varied a lot of parameters. I varied the frequency, I varied the volume. I had different setups, so I think I really varied the relevant parameters for this problem. And to state again, the task statement states to investigate the phenomenon and not to vary things like viscosity. And I said it is important to state that surface tension and viscosity are basically mainly important boundary conditions that make this phenomenon possible. So you have the critical length that is required, and there basically I explained that surface tension goes into that and is basically inserted in the boundary conditions, and I explained the effect of viscosity, but I said they don't have then a major effect in reproducing the phenomenon. I think that's something the opponents spent a lot of time on. I think that's a shame because there would have been other interesting things to talk about. So yeah, so as said, I think bubbles are mainly negligible effects, and I think that's also what the reviewer said. And importantly, gravity cannot be neglected, as the reviewer pointed out. It basically, gravity plays into the effective gravity, and it's a major thing. So it's basically what pulls the fluid downwards. So you have got the gravitational force. If there wasn't, it would just levitate in the air, you know. Sure, if you don't have gravity, why do the problem? Right? But as said, I had like a great setup that enabled this variation. I had like this harmonic oscillation that was very stable and reproducible. I used silicon oil, which was the ideal liquid for this case. I had an accelerometer to precisely measure the acceleration. And as I said, I could go into different frequencies and different accelerations. I had reproduced the required setup, so I injected it from below, as said, with a stable container.
Okay,
but also I said
much.
it from above, and I said there's I had like my.
Thank you very much for this. So now we have time for questions from the jury. Is there any questions? Yes, please.
So I have a question. Can you go, so when you have your measurement, you get this very bumpy shape of the liquid on the top and the bottom as well, but when you explain the phenomenon, you describe it as a wavy surface.
Yes.
And I don't really see how a wavy surface applies to your
So
phenomenon.
I have to explain that when you have a large container, so with where the fraction of the liquid that is basically at the border, that doesn't play an effect. So those are boundary conditions that disturb the small. That's why I went to a larger container where you can clearly see that this portion is not as big. So it's really a question of scaling. So you have it for a specific distance from the border, and then those effects are minimal.
Okay.
Yes.
Well, the problem said that the fluid has to be partially filled in the container.
Yes.
Did you investigate about the fraction that is needed to produce the phenomenon?
So, I mean, if you have the container completely filled with liquid and there's no air from below, it will be way harder. You are basically injecting air in it, so it will stay below, it won't rise because there's like no pressure difference. So if you have already a very high pressure in the system, this will affect the system greatly. So you will have to basically push the air into something that's already filled. So we have basically a free surface on top with like an anchored pressure and the normal conditions of air, and that's basically what we have. So it's partially filled with liquid.
Thank you.
Any more questions? Yeah.
I have a question. Can you go to the slide where you compare your theory to your
Yes.
measurements?
Yes. Can you state the question and then I?
Yes, so I have several, but one is like, I don't understand why the red point changes with the frequency, and also I didn't catch what your justification is for the quite large difference with your theoretical
Yes.
prediction.
Okay, so that basically shows the amplitude over the frequencies, and when you have very high frequencies, the amplitude scales proportional to that. So you have smaller amplitudes of the oscillations that very, very fast on those. So that's basically the driving acceleration on the lower surface that matches the acceleration of the setup. And then afterwards, as you can see, the theoretic line is above that. So it basically models the the amplitude that you would have on the interface between the liquid and the air, so on the unstable state. As you can see, it's lower than what we actually have, and that's because of the effect of the air cushion. So the effect of the air cushion that basically increases this amplitude, so maximizes this acceleration of the system, is not taken into account in this model. So it basically only takes this the effect of the gravitational offset.
Okay, thank you.
How do you quantify the term stability in your work? You
What?
talk about the stability
Yes,
in your work,
so-
but how do you quantify it from the
So
experiment?
here, as you can see, I basically I put a certain acceleration and then injected the air so that I get this levitating state, and then I went down with the acceleration so that basically I tried to see at which point, at which acceleration the system breaks. So the stable state, so the levitation breaks, and the upper layer basically goes down. So when it destabilizes everything. So this is basically shows the minimal acceleration needed to basically reach the stable state. So
Yeah, but how do
above
you
that,
quantify
everything is
stable?
stable.
How do you say it is stable?
When it will remain, I said it will I measured like more than an hour in time, it will remain in the stable state. So after you have it, it's extremely stable and reproducible
Thank
on
you
all
so much.
conditions.
Yes, please.
So for the reporter, how did you inject the air inside your container? By syringe, but with your hand?
Yes, so I pushed it like what? So as you can see with the setup, I fixed the volume of air I had here, and then I gently pushed it inside, so into that.
Okay, and
So as you can see there,
do
and
you
there was like this tube like from.
okay, and do you believe that the rate of the air injection affects your whole phenomenon of levitating fluid?
So if you basically push it faster, you will have already this initial. You give the air bubble basically
Short
this
answer.
push to. So it's faster, so it's harder to get it to levitate. It will basically, the buoyancy will be stronger, and it will basically go up faster. So
Okay.
you want to minimize. Thank you.
Thank you very much. Thank you all. Okay, so let's continue to announcing the grades for the reporter. For the report, we got 3, let's see, 4, 4, and 3, 4, 4, 4, and 6. For the opposition, we have 4, 5, 6, 5, and 4. And for the review, we got 8, 7, 7, 7, and 6. Okay, so for the report, I got the single 6, I think, which was the highest, on the higher side. Well, my partial grades are 3, 1.5, and I rounded up to 6. I liked the report itself, so it was very clear to follow, and it was an interesting solution. It was not, I mean, it was fairly good done. For the discussion, I would have expected some more kind of leading through the discussion on your own too. I mean, of course, it's the task of the opposition, but if you see that we are discussing lots of time on a certain point, you could also suggest to head on to something else, because otherwise it's kind of, you get stuck into the discussion somewhere, and there were several other things to discuss, so that was one point I would criticize. But overall, I was quite happy with the report. Also, of course, it could have been investigated even further, but that's always the case. Maybe the lower grade of
Well, actually, at first I about to give 4 because of like this is an average presentation, but I deduct the score like 0.5 from the jury question because your answer is quite long and doesn't address the question that I asked. And well, in general, I give the partial score like 1 plus 1.25 plus 1.5 and minus 0.5. So it will be 3.25 and a round down. And in terms of content, I would say that the problem asks you and put the quotation mark to the term levitate. And if you read the article related to this phenomenon, you will see that they describe the problem sinking bubble, which is 2019. The year I participated in IYPT, so I know that problem well. And I expect that you will mention it in your presentation, but you mainly focus on the stability, which is not even mentioned in the problem statement. So I would say that I will give you a high score in terms of content if you focus more on the replication of the theory.
Okay, thank you. So for the opposition, we got what was the highest grade for the opposition?
6 from
A 6. Yeah, could you please comment on the 6?
So for the opponent, you started with good questions. It was relevant, okay, and your presentation presented some of your points. I'm not sure that it was the perfect prioritization for me, and but it was okay. And after that, in the discussion, you raised some topics, and you present some of your own opinions better there. Yeah, sometimes you focus to some things and we didn't have a good flow in the discussion, but overall it was a good discussion, good opposition for me. So,
Thank you. So I was on the lower side. Is there another 4? No, I was the only one.
Yes, there was another one.
There was another 4. So maybe you could, but we too commented, so I don't know. What do you want to?
How can you?
So I will comment on it. Maybe you can comment afterwards. What I liked was the opposition speech. It was quite good. For the questions asked, for me they were not. I gave 0.5 for that. They were not so relevant for me. And what I disliked most in this case was the discussion with the reporter, because you stuck so many times to single aspects, and I would have found it better to lead through more topics. And above all, to present your own opinions. It was sometimes more like a question-answer style, but I didn't get your own opinion, why you asked the question, why you want to discuss this topic. That was what I was missing most. Don't know if you want to add something.
Yeah, we act exactly the same because I give you the low score for the discussion with the reporter because most of the time you allow the reporter to take the space a lot. I mean, allow to explain the really long answers and that you do not stop. And then when you finish the discussion, you do not conclude whether you have any suggestion, any opinion about those topics that you already discussed. Yeah, that's the only point that I made this score quite low for your presentation, for your performance.
Okay, thank you. So for the review, we got, I can't remember the number.
8.
An 8, yes, please.
Well, I mean, a lot of questions that I list and about to ask the reporter and opponent, you already addressed them, so I almost ran out of the question that I want to ask them. So I get a lot of points for the question asked by the reviewer. And then for your evaluation of the report and the opposition, I think that you do a lot of, you do a very good job. You can mention a lot of points related to their discussion about the point that they raised and about their weaknesses that about the sinking the bubble that sink and not rise in the normal cases that you mentioned. So I think that you do a very good job and I give a very high score for that.
Okay, and the lower end was 6, I think.
Yes, what?
1. So it was me again. Sorry for you. Okay, so my partial grades are 1.5, 2, 1, and 0.5, and no subtractions or add-ons. So yeah, the main problem was time management because the review of the opposition was already quite in a hurry, and discussion analysis was kind of missing somehow because there was no time left. So that's the reason why I had to subtract something there. Also, I found that your review of the report was very good, and yeah, and I could see that you had a good insight into the problem, but I couldn't grade higher. Okay. Anyone wants to add something, or? No, thank you very much for this nice day. So let's take a break for 15 minutes.